when we are studying acid-base chemistry, we talk about the concept of conjugates, conjugate acids and conjugate bases. And that means they are the species associated with when that acid or that base react. So for example, if you have an acid and the acid reacts and liberates hydrogen ions, then it releases the corresponding anion in solution, and we call that anion a conjugate base. And in the case of here, you've got a base accepts hydrogen ions from the acid, so it forms this other species in which has accepted the hydrogen ion, and we call that the conjugate acid. We call those conjugate pairs, and you often see them written, for example, HCl and Cl minus, and that means they are a conjugate pair. Hydrochloric acid is the acid and the chloride anion is the conjugate base. Or you might see, for example, another common one is NH3, NH4+, the ammonia-ammonium conjugate pair. Ammonia is a base, the ammonium ion is the conjugate acid of ammonia. I'm going to ask you to stop the video and have a go at this exercise. Could you identify the conjugate pairs on these two reactions? Stop the video now, please. Okay, if I look at the reaction, I can immediately identify that I've got HBr, which is hydrogen bromide when it's in gas form, or bromidric acid when it's in solution, as here it says it's in aqueous form. And I can see that it reacts to produce this bromide anion. That means it has lost a hydrogen ion, this species H+, and we'll talk more about if it exists or not in a few slides. So then this is my acid, and the bromide anion will be the conjugate base for the bromidric acid. And in the case of the water, I see that from the reagent to the product side has accepted one hydrogen ion. That means it has behaved like a base. And the H3O+, which is, we also call it hydrogen ion, and we'll talk about more in a future slide, is my conjugate acid for the water. If I look at the second reaction, you might not recognize the chemicals. I've got this HPO4 2-. This is called hydrogen phosphate anion. And this group here, PO4 3-, this is called a phosphate anion, or the phosphate group. So if I look at the HPO4 2-, this hydrogen phosphate anion, I can see that it has lost one hydrogen ion, one H+, and that means that it's now an extra negative charge that is not compensated by this H+. It has less electrons behind and has formed the phosphate group, the phosphate anion. That means that because it has lost a hydrogen ion, it has donated a hydrogen ion, it has behaved as an acid. So the hydrogen phosphate is the acid, and the phosphate group is the conjugate base of the hydrogen phosphate. And then if I look at the water in the reagent side and the product side, in the product side, the water has gained one hydrogen ions. That fits with the definition what a base does. So the water here is behaving again as a base, and it liberates its conjugate acid, which is the hydrogen ion. If you notice the difference between the first and the second structure reactions, well, there are a couple of things that spring to mind. One, here I've used one arrow going right from the reagents to the products. This one I've used the double arrow, and that means I'm implying that this reaction does not fully go to completion is called in what we call an equilibrium. The reagents are reacting to make the products, but the products are also reacting to give back the reagents. And we'll look more about what that double arrow means in a later slide. Also, you might notice that when I look at this compound, this is a neutral compound, I can totally imagine having bromidric acid in a bottle and make it react with water. But when I look at here, HPO4 2-, it has two negative charges. There is something missing there. It's as if I had caught the reaction halfway through. There is missing something because you don't have anions or cations existing on their own. They are always, matter is neutral. So I am missing something there. So more about what's missing in that HPO4 2- in a future slide.